Assume there's an object very close to the concave mirror. Fine. And you imagine rays from the object striking the mirror. One ray will be like this, it'll get reflected straight back. Another ray will go like this. See, this is very close to the mirror. I mean, suppose the center is here. Okay, it's closer than the center. Then another ray may strike like this and get reflected this way. Another ray may strike like this and get reflected maybe like this. Okay. So you can see that there is a significant angle of divergence between the rays that strike the mirror. Okay, there's a large angle actually. Fine. As you take the object away from the mirror and you visualize the rays striking the mirror, okay, it'll get reflected this way. Fine. And one ray like this gets reflected this way. You can see that the angle of divergence between these rays that strike the mirror, Rishi, tell me, has it increased or decreased? Like
Increased, sir.
compare the rays diverging from the orange dot and the rays diverging from the blue dot, which have a lesser angle between them. Which rays have lesser angle between them?
The blue one, blue
The
rays.
blue one. So it has decreased. As we take the object far from the mirror, the angle of divergence of the rays that strike the mirror decreases, the maximum angle of divergence. Okay. Now, Rishi, you imagine it like this. Suppose the object is continuously moved back up to infinity. Okay, if object is very far away from the mirror, what will be the angle of divergence, maximum angle of divergence between the rays that strike the mirror? If the object is taken very far away from the mirror.
180, sir.
Is it increasing or decreasing? Is the angle of divergence increasing or decreasing?
Decreasing, so it should be 0.
It tends to 0. Okay. It's important to imagine what happens to the rays. So let's visualize a very small mirror, actually large mirror only, but if the object is very far away, then compared to the distance between object and the mirror size will look very small. So consider something like this. Okay, let's say this is the concave mirror. And the object is very far away from the mirror, maybe somewhere here. Okay. Now from that object, if you imagine rays incident onto this mirror, like the extreme rays, if you consider the first one and the last one will be like this. The last one that strikes the mirror will be like this. Okay, there's a very small angle between these rays you can see. So as the object goes to infinity or very far away from the mirror, the rays from the object which fall on the mirror almost become parallel to each other. Okay. So if the object is at infinity, the incident rays, the rays that strike the mirror, will be parallel to the principal axis. That is why we say focus is the point of convergence of reflected rays when incident rays are parallel to each other. Now, how do you get incident rays which are parallel? You keep the object very far away from the mirror. So consider one ray like this. An incident ray parallel to the principal axis. It's coming from an object which is infinitely far from the mirror. Then you draw a normal, and we had discussed that you should get used to this actually. How you draw a normal to a spherical mirror or lens is you connect the center of that spherical surface to any point on that surface. So the point of incidence, that becomes a normal. An angle of incidence should be equal to angle of reflection. If you ensure that, you will see that the reflected ray passes like this. Okay. You can take as many parallel rays as you want. Okay. Consider another ray parallel to the principal axis like this. Basically, these are rays which have diverged from an object which is at infinity. Okay. I am assuming there is a blue dot at infinity, blue point object at infinity. another ray like this. Again, you can imagine the normal. These are all common things only. This is the normal. Then you draw the reflected ray, making sure that the angle of incidence is equal to angle of reflection. You'll see that the reflected ray passes somewhat like this. Fine. So this is the point where the reflected rays are meeting. So if object is at infinity, this becomes the image location. And when object is at infinity, the image location is what we call focus. Okay. So this becomes the focus of the concave mirror. And according to what we derived in the last class, the focal length is nothing but distance from the pole of the mirror to the focus. Now this point P is the pole. Pole to focus is what you call as focal length. Focal length will exactly be half of the radius. Okay, we have derived that in the last class. Right. And when you draw the ray diagram also, that is what you see. And remember, the focus of a concave mirror. Okay, this is a concave mirror, right? The focus of a concave mirror is in front of the mirror. And one more thing you need to remember, when a ray is incident parallel to the principal axis, after reflection, it passes through the focus. This idea is important. It helps us in drawing ray diagrams of extended objects. Okay. So focus of a concave mirror lies in front of the mirror. Next, consider a convex mirror. For a convex mirror, the center is behind the mirror. Maybe somewhere here, the center of curvature. Imagine rays from a distant object. Object is very far away, okay, at infinite distance. Incident on it. When rays are coming from infinite distance onto a finite mirror, the rays will be parallel to the principal axis. Okay. Draw a normal there. To draw a normal, you join the center of curvature of the mirror to that point and you extend it. So this becomes a normal at that point of incidence. And you maintain angle of incidence is equal to angle of reflection and draw the reflected ray. Okay. The reflected ray will be somewhat like this. Okay. You can consider another incident ray anywhere. You can take it on the upper side itself, not a rule that you have to take it on the lower side, but I'm taking one on the lower side. Another ray incident parallel to the principal axis. Again, you draw a normal there. Just connect center to that point and extend. That becomes a normal automatically. And then the reflected ray, ensuring that angle of incidence is equal to angle of reflection. You draw the reflected ray, it will be like this. Okay. Now you can see that after reflection from a convex mirror, the rays are diverging. So they are not going to meet in front of the mirror, but we want a common point from which these rays pass. So what we do is we extend them in the backward direction. And you extend both of them in the backward direction, the point where they intersect becomes the image location. Object is at infinity, this is the image location. And when object is at infinity, the image location itself is called the focus. And again, the distance from pole to focus is what you call as the focal length. Okay. So remember, for a concave mirror, focus will be in front of the mirror. Center and focus will both be in front of the mirror. For a convex mirror, center and focus will both be behind the mirror. And focus will be at half of the radius. So it will be exactly between pole and center. Okay. But remember, focal length f is equal to r by 2 is derived using the mirror formula. Okay. We assume object is at infinity. Then we get image distance as r by 2. Therefore, the focal length becomes r by 2. Can one of you quickly tell me the condition under which the mirror formula is valid? Like 1 by v plus 1 by u is equal to 2 by r. For what kind of rays is it valid? Or what is the approximation we made while deriving that? Okay, we considered paraxial approximation, means the rays striking the mirror should be very close to the principal axis. Fine. Only rays which are very close to the principal axis will pass through a common point on the principal axis after reflection. In fact, that is also not a common point, but the point where they meet the principal axis after reflection will be very close. If incident rays are very close to the principal axis, such rays are called paraxial rays. Okay, this is actually an exaggerated diagram. The point of incidence A cannot be that far from the pole for the mirror formula to be valid. Okay, the rays should actually be very close to principal axis, somewhat like this. Then they will all pass through the same point after reflection. If rays go very far away from the principal axis, if rays make a large angle with the principal axis, incident rays, reflected rays won't pass through a common point. Okay, they won't even pass near a common point. Fine. Now, since 1 by v plus 1 by u is equal to 2 by r is valid only for paraxial rays, this focal length will also be valid only for paraxial rays. And as far as your syllabus is concerned, when an object is placed in front of a mirror, or when you are asked to find out the image distance from a mirror, you will assume the rays are paraxial only. Okay. So here also you get focal length is half of the radius. It will be exactly between the pole and the center. But remember the condition that is true only when the rays are close to the incident rays are close to the principal axis. Okay, so how do we make use of this point called focus? Basically, when a ray is incident parallel to the principal axis, okay, like this one or this one, when it is incident parallel to the principal axis, after reflection from the mirror, it passes through the focus. Okay, let's see how this can be used to draw the images formed by images of extended objects formed by a concave as well as a convex mirror. Consider a concave mirror itself. Let's say its focal length is f. Okay, we want the ray diagram first. Assume the center is somewhere here. And let's say there's an object placed here. We'll assume the size of the object is small compared to its distance from the mirror. Okay. Or let's take the object like this. We want to find out what kind of image it will form. Okay, let's look at an example, just a moment. Look at this picture. This is the picture of a hand, person's hand, placed in front of a concave mirror. Okay, spherical concave mirror. You can see the person's actual hand. This is the actual hand. And this is the image that we see in the mirror. Can you tell me the differences between the object is the person's actual hand, and the image? How is the image different from the object?
That it's the size of the image is bigger than the hand.
Okay, so it's an enlarged image. And any other differences you observe? Is it inverted or is it of the same orientation as the object?
The same orientation.
Same orientation. Okay. But you look at the other things that you see in the mirror. There is a bench that you can see. Okay, I hope you all are able to notice that there is a bench here. Now that bench is behind the person, probably behind the person. And bench normally will be in its proper orientation, but the image that you see, image of the bench that you see there, how is it?
It's
Do you,
inverted, sir.
do you think the bench would actually have been like that, or is it an inverted image? It's inverted. Okay. The hand's image is not inverted, but the bench's image is inverted. And clearly, the bench will not be smaller than the person's hand, definitely. But in the image, it looks very small. So is it an enlarged image or a diminished image? Clearly, it's a diminished image. Now, both the images are seen in a concave mirror itself. So it's possible that a concave mirror forms enlarged images, enlarged and upright images, upright or erect. Okay, it can form images like that. It can even form inverted diminished images. Okay, so let's see how all this happens through a concave mirror, or how a concave mirror can do all this. Okay, so what we have taken here is an object placed well beyond the center, as you can see. Now rays from the object strike the mirror and get reflected. We need to find out the common point through which the reflected rays pass. That becomes the image location. Okay. Now let us consider the tip of the object. Let's call the object as AB. Bottommost point is A, topmost point is B. Okay, object itself is O. Okay. Now, to find out the point of intersection of the reflected rays, we need at least two incident rays. From a common point of the object, we need two incident rays. We'll see how they get reflected and where they meet. Okay, so this is, I'm teaching you the basics of ray diagrams, how to draw ray diagrams in optics. Okay, let's consider the tip of the object, upper tip of the object. We need to draw two rays onto the mirror, or draw two incident rays onto the mirror, such that it will be easy to draw their reflected rays. Now you can take incident ray whichever way you want. Okay, you can draw an incident ray from the tip of the object to this point. You can draw an incident ray from the tip of the object to this some random point here, some point here, as you wish. Okay, but we need a diagram as accurate as possible. Okay, so it should be easy for us to draw the normal. It should be easy for us to draw the reflected ray. Fine. For that purpose, we can use these incident rays. Can any of you tell me, how shall we draw the incident rays such that it will be easy for us to draw their reflected rays? I mean, we can draw the reflected rays very accurately without using protractor and all. We can maintain angle of incidence is equal to angle of reflection.
So
Okay.
taking a ray, incident ray from the tip of the object.
Rishi, can you repeat?
Like we can take the incident ray from the tip of the object.
From the tip of the object itself, where should it strike the mirror, or how should it travel towards the mirror? Okay, Pradyun is saying one through the focus, one through the pole. Okay, okay. See, we have just learned that if incident ray is parallel to the principal axis, Rishi, tell me what happens to such a ray after reflection? If incident ray is parallel to the principal axis, how will the reflected ray pass?
So it will converge towards the center.
Center. Why will it go through the center? If incident ray is parallel to the principal axis, look at this diagram and Rishi, tell me, how does the reflected ray pass?
It passes through the focus.
Through the focus. Okay. And we know focus is exactly between the center and the pole. So this is the focus. The reflected ray passes through this point. That is how it becomes easy for us to draw the reflected ray in this case. If you take an incident ray parallel to principal axis, you don't even have to draw the normal, use a protractor and maintain angle of incidence is equal to angle of reflection and all. You can easily just draw the line, draw the reflected ray through the focus. Simple. Okay. Another incident ray for which drawing the reflected ray will be easy is the ray drawn straight to the pole of the mirror. From the tip of the object, same tip, same point on the object, you draw an incident ray straight to the pole of the mirror. So like this. Rishi, tell me, how is it easy to draw the reflected ray in this case? Okay.
Sir, I'm not sure.
No problem. The principal axis is the normal drawn to the mirror through the pole. Rishi, do you agree with that or not? For the second ray that we have taken, second incident ray, is the principal axis itself the normal or not?
Yes, sir, it is.
The principal axis itself is the normal. So the reflected ray will just be the inverted version of this incident ray. So what to do? Mark this point such that this height above the principal axis is equal to this height below the principal axis, and then draw the reflected ray easily like this. Make it pass through that point. Simple. Okay. The incident ray and the reflected ray will be symmetric about the principal axis. Okay. We got the image location now. Whose image is formed? B's image, because these two incident rays were taken from the tip B of the object. From that tip, when rays are incident, they seem to be meeting here. So this, I'll call this point as B dash. Okay. Now from the lower end of the object A also, if you take incident rays and draw their reflected rays, you will see that they will pass through this point. Okay. Therefore, this is the image now. We have drawn incident rays only from the upper tip of the object, not from the lower end of the object. But at the same distance in front of the mirror, the lower end's image also will form. So A dash, B dash, this becomes the image location, I. Okay, hope this is clear to all of you. It's very important to draw ray diagrams like this. Okay, and what we now need, you can see, okay, Rishi, you only tell me. Object is AB, image is A dash, B dash. What kind of image is this? Is it inverted or upright? Erect.
Inverted, sir.
Inverted, clearly. Is it enlarged or diminished compared to the object?
Diminished.
Diminished. Okay. That is what has happened with the bench that you see here in the image. So we can guess that the bench must have been present beyond the center of the concave mirror in front of it. Okay, because it has formed an inverted diminished image. Right, so that is how a concave mirror forms an inverted diminished image of an object. Okay. But we still have to think of how the hand's image is formed upright and enlarged. We have to explore that possibility also. We'll do that. But let us derive a formula for magnification now. Okay, we know we got the image smaller than the object. We define magnification of a mirror or a lens, okay, or a spherical surface. We define magnification as height of the image divided by height of the object. How big is the image compared to the object? That is how we define magnification. So in this diagram, magnification is nothing but A dash B dash divided by AB. We need that ratio. Okay, let me copy this diagram. Now you can see that AB and A dash B dash are two sides of similar triangles. One is this APB is one triangle, and A dash P B dash is the other triangle. These two are similar triangles. Which rule of similarity do they follow? Like there are different kinds of similarity between triangles, no? Which, according to which rule are these two triangles similar? Okay, there's something called angle, AAA similarity. If all three angles of one triangle are equal to all three angles of the other triangle, not, I should not say all three equal to all three. If every angle of one triangle is equal to the corresponding angle in the other triangle, then we call them similar. Now we know that angle of incidence, okay, call this as I, is equal to angle of reflection, common angle. And there's a right angle here, there's a right angle here. If two angles are same, then automatically the third angle will be same. So these two are similar triangles. And in similar triangles, the ratio of corresponding sides is equal. So we can say that AB divided by A dash B dash is equal to OP, or I'll say PO divided by PI. PO is the object distance, PI is the image distance. Okay. Is this clear? Any doubt in this? How I wrote this statement? AB by A dash B dash is equal to PO divided by PI. You can also call it PA divided by PA dash. That's the same. Okay. I is nothing but I is at A dash itself. Image has formed at A dash. Okay. So this is from similarity of triangles. Now, in this case, in this particular case where the object is beyond the center in front of the mirror, image has formed at this position and you know what kind of image it is. And this way you can find out the magnification. But we want a formula for magnification which works in all cases, not just in this particular case for a concave mirror object placed beyond the center. Okay. So according to the rules of sign convention, we know that anything or any distance above the principal axis is to be considered positive. Any distance below the principal axis is to be considered negative. Okay. So the magnification in this case, which is basically height of image by height of object, will be AB divided by negative of A dash B dash. Okay. That is PO divided by negative of PI. PO is object distance. Okay, wait, magnification is height of image by height of object. No, we have to invert this. Image is A dash B dash divided by object is AB, and image has formed below the principal axis. No, so we'll put a negative sign to this. That distance has to be considered negative. Now, if you look at it as a side of a triangle, sides of triangle are always positive, but we are applying a sign to it now. So minus A dash B dash by AB, that becomes minus PI divided by PO. PI is nothing but the image distance V. PO is nothing but the object distance U. Therefore, magnification of a mirror is given by the formula minus V by U. Now, we derived a formula just by using the distances, the sides of a triangle and all. But we converted it into a form by applying the rules of sign convention. We converted it into a form which will be applicable in all cases, not just in this one case of object present in front of a concave mirror beyond the center. Okay, you can use it in any case. Fine. So this is the formula for magnification produced by a mirror minus V by U, where V is the image distance, U is the object distance. Okay. So the mirror formula is 1 by V plus 1 by U is equal to 1 by F. You can write it as 2 by R also. And the magnification produced by a mirror is minus V by U. And remember, both these formulas can be used in any case of mirrors, in any case of object placed in front of a mirror, by following the rules of sign convention. So you must substitute following the rules of sign convention. Okay. Again, let's go back to that image that we saw in the concave mirror. The bench's image, which is inverted diminished, is explained. We can say that the bench must have been placed beyond the center of curvature of the mirror. That's why its image is like this. But look at the hand's image. Now the hand seems very close to the mirror. Okay. So close that it might be between the focus and the pole. The hand seems to be between the focus and the pole, very close to the mirror. And you can see how its image is formed. It's an enlarged image and it's upright or erect. Okay, let's see how that case is possible. We have to consider an object within the focal length. So consider something like this. Solve this as a problem, all of you. Assume the radius of curvature of a mirror, concave mirror itself. We still have not discussed convex. Radius of curvature of the concave mirror is 20 centimeters. And object is placed. Okay, if radius is 20, half of it, focal length will be 10 centimeters. Object is placed, let's say, at 5 centimeters in front of the mirror. Okay, calculate image distance and calculate the magnification of the image produced. Do this, all of you. It's very important to visualize the ray diagram also. Radius of curvature is 20 centimeters. Object is placed 5 centimeters in front of the mirror. Let's say this is the center. This is the focus. And object is here. Okay. Rishi, tell me, how do we do ray tracing? How should we draw rays from the object onto the mirror?
Sir, from the tip, and then it goes parallel to the.
Okay. From any point of the object which is not on the principal axis, we take one ray parallel to the principal axis. Fine. How does it get reflected? Or how does it pass after reflection? This ray. It passes through the focus. If the incident ray is parallel to the principal axis, after reflection, it passes through the focus. So one ray goes like this. And we take another ray straight to the pole of the mirror. From the same point of the object, you take a ray directly to the pole of the mirror. How does it get reflected? It gets reflected symmetrically about the principal axis. So after reflection, this ray which strikes the pole of the mirror passes like this. Now the two reflected rays clearly are not going to meet in front of the mirror. They are diverging. So if you want to find out the common point from where they are originating, or the common point where they appear to be coming from, you'll have to extend them in the backward direction. Do that and you will see that to any person in front of the mirror, these rays will appear to be coming from somewhere here. So the tip of the object, its image, the upper tip of the object, its image is formed here. Then the rest of the object's image also will form here itself. This is the overall image that you see. And if this is object, this is image. Now see the kind of image that has formed. It's an enlarged image, it is upright, and it has formed behind the mirror, so it's a virtual image now. So a concave mirror can do this also. It can form enlarged images. Pradyun is asking, sir, we select the rays based on which is easiest to show where the image is formed, right? We draw incident rays based on how easy it is to draw the reflected rays. Okay, that's why we take one incident ray parallel to principal axis. Reflected ray will pass through the focus. No, we can easily draw it off. Okay. So, and another ray we take to the pole of the mirror, and reflected ray will be reflected symmetrically. If the incident ray strikes at the pole, then you just have to draw a symmetric ray below the principal axis. That will be the reflected ray. Pradyun is asking, we can also take the ray through center. See, taking ray through center will work, okay, because if any incident ray passes through the center, suppose there's an object here, you take an incident ray through the center, any ray passing through the center, when it strikes the mirror, it gets reflected straight back. That itself will be the reflected ray. Very easy to trace. You don't even have to draw the reflected ray. But there is a risk in this, because this will work only if the object is beyond the center. If object is here, there's no point drawing the incident ray this way. Okay, so that will work only in cases where the object is beyond the center. So it's better to avoid it. Yeah, if you're comfortable and if you can remember all the cases, you can. Okay. So yeah, this is what must have been happening with the hand that you see in the image formed by the concave mirror there. The actual hand, which is the object, is very close to the mirror. So it must have been within the focal length, and that is how the image is getting formed. You get an enlarged image which has the same orientation as the hand, as you can see. Okay, so it's an upright image and it's formed behind the mirror. So see, in front of mirror, behind mirror, you cannot properly appreciate in this photo. Okay, but if you look at it really, then you can understand whether the image is closer than the mirror or beyond the mirror. Okay, in this photograph, it's not clear whether the image is formed in front of the mirror or behind. Like that desk, that bench's image and the hand's image. You can't tell which is in front of the mirror, which is behind the mirror by looking at this photo. In a real life situation, you can. Okay. Fine. So first case we discussed was when the object is beyond the center. Image forms between center and focus. Okay, remember these cases. If object is beyond the center, image forms between center and focus. And what kind of image is this? This is a real image because it's forming in front of the mirror. You can reverse this case. What I mean is, if this becomes the object, if you bring the object to the image location, image will go to the object location. This becomes its image. Okay, you just have to draw the rays in reverse. That's all. Okay, so if A dash B dash is the object, then AB becomes its image. Now, what kind of object, what kind of image does it become? You can see A dash B dash, the arrow is below the principal axis. AB, the arrow is above the principal axis. So it's an inverted image and an enlarged image. Fine. So if you take this as the object, this is the image, inverted diminished. If you take this as the object, this is the image, inverted enlarged. That is also possible with a concave mirror. Okay. And if you take this as the object within the focal length, then this is the image, upright enlarged. But in this case, it's a virtual image. These are the three possible cases of image formation by a concave mirror. And remember this point also, when object goes to image location, image will come to object location. They'll switch places. But that is true only if the image is a real image. In case of virtual image, if you take the object to the image location, you won't get anything at all. Okay, what I'm saying is, look at this diagram, ray diagram. If you take object to the image location, okay, where is the image now? Behind the mirror. If you take the object here, the mirror won't even form an image. Okay, well, how can the mirror form an image of something which is behind the mirror? Okay, so in case of virtual image, object and image won't switch places. Okay, but if object is real and image is real, then you can interchange their positions. If object comes to image place, image will go to object place. And I used one term here, object being real. That also we will discuss. Okay, fine. Let's solve some problems based on this. Okay, in this case, I asked you to calculate the image distance. No, Shashank has given the answer. Just a moment. You got image distance as plus 10 and therefore you said magnification is 2. Okay, fine. You apply the mirror formula. Let's assume plus 10 is correct. Image distance is plus 10 means it's formed on the positive side. Now, which side is positive? It's determined by the direction in which the incident rays are traveling. Incident rays are traveling to the right, so right side is positive. Anything to the left of the mirror is negative. Okay, fine. And the basic formula for magnification produced by a mirror. Formula is minus V by U. And in this, you are supposed to substitute V and U with proper sign convention. Now we got V as plus 10. We'll put it as it is. U is the object distance. Object distance is the distance from pole to the object. Object is in front of the mirror is negative. So object distance is negative here, minus 5. Minus 10 by minus 5, you get a magnification of plus 2. Okay. Now, there are two components of this magnification, the plus sign and the 2. The plus sign indicates the orientation of the image relative to the object. Positive orientation means upright image, same orientation as the object. Had magnification been negative, it indicates inverted image. Okay, here it's an upright image, we know that. And the 2 here is the magnitude of magnification. How many times bigger the image is compared to the object. Okay, so it is the magnitude of height of image by magnitude of height of object. Okay.